Okay. And finally, I would like to introduce Jana Glivicka. We're in a sort of temporal squeeze in this conference, but obviously we'll finish later. So Jana Glivicka, she's here as a part of this experiment to make dialogue actually mathematicians and philosophers. So she teaches at Charles University at the Faculty of Mathematics and Physics, where she teaches logics and set theory. And she will try to present us some of the basic principles of the set theory, because we think that obviously this is the part of Badiou's work which is like probably most hard to understand for philosophers. And we just spoke about it during our lunch, that actually an interesting experiment to organize maybe next year would be to create a dialogue between mathematicians and philosophers, so that we can actually ask you some questions on set theory that may help us to understand better Badiou's work. So, as I say, I would like to thank Jana for her courage, and we're back to courage, to take part of this experiment.
Okay, so thank you for inviting me, but I will have to do presentation on. How do I do that? Okay, because there is no way a mathematician can give a talk without a presentation or a blackboard. So
you can actually probably use this if you need blackboard. Jana.
I think it's all.
That's this.
I don't know how to put it on full screen, but I think you can see it, so it's fine. I will just have to be clicking like this. Yeah, it will be okay. Okay, so I will be obviously speaking about set theory, and the reason or the thing that is interesting for me in Badiou's work is this connection of set theory and philosophy. And I think it might be very confusing even for philosophers as well as for mathematicians. You can ask, where does the set theory end and where does the Badiou's philosophy begin? And this is one thing I want to accomplish with giving this talk is just give you a very general and very vague idea what really is a set theory, or how mathematicians think about set theory, and maybe it will help to clarify this problem. So, I told you I will be talking about set theory, but it's a theory of triangles, right? It is weird. There is nothing in mathematics that could be called a theory of triangles. This is just a stupid examples of me to give you flavor of those multiple views I will be talking about later. So, if you were asked to give a theory of triangles, what could you do? Well, you could say, obviously, there should be an axiom of this theory that says there exists some triangle, right? Because without triangles, you can have no theory of triangles. So this might be this axiom. There exists capital A, B, and C, and think about those as the vertices of the triangle. And there is a small a, b, and c. Think about those as edges of the triangle, such that the edge C connects A and B, the edge A connects B and C, and so on. This is a triangle, right? So, if you were asked to give a model of such a theory, you could obviously draw a triangle like this. You have three edges, A, B, and C, connected by, three vertices, A, B, and C, connected by three edges, A, B, and C, and obviously the edge C connects the vertices A and B. So it's an example of a triangle. But I can cheat you a bit, because I can say, okay, this is also an example of a model of the theory of triangles. But notice that the capital A is now an edge. It's not a vertex, it's not a point. But in the axiom, I don't say anything about A being actually a vertex. It's just the way we think about this A. We just think about it as being a vertex. So if I draw a picture like this, it's the same picture. I just rename those 6 elements. It is a perfectly good triangle. And now, from my point of view, this capital A is an edge. But from the viewpoint of the model of the theory, it's a vertex. Because capital A is a vertex, right, in some sense. So I will just keep switching viewpoints like this. And I know it can be very confusing. So there's one more example of a triangle. It doesn't look like a triangle at all, right? But it is a triangle because I have 6 objects. This A, B, and C, and this small a, b, and c, and this small c connects A and B, right? Just exactly what I demand for it to be a triangle. So in a sense, this is a triangle, or rather, it can be thought as a model of the theory of triangles. Okay? Something much worse can happen, and actually something much worse will happen in set theory. So imagine you lived in a world of triangles. What I mean by this, if you are living in a world of triangles, any object you encounter is a triangle, like by definition. So you live in this world of triangles, and you are asked to give a model of the theory of triangles. Well, obviously you would have to draw something like this. You have no lines and points, so you cannot draw the regular triangle. But if you draw this object, it is, in some sense, a model of theory of triangles. It has 3 objects, capital A, B, and C, that play the role of vertices of a triangle, and I have 3 objects, small a, b, and c, that play the role of edges of the triangle. And kind of it satisfies the axiom of existence of a triangle. And now we get to the main point of my talk. There are different views of this picture. From the viewpoint of the model, as I already said, the object A is a vertex. Why is it a vertex? Because it is connected to another 2 vertices by some edges. So it is a vertex. And the 6th tuple of the object is a triangle, because it's kind of our definition of triangle. Triangle is a 6th tuple such that the 6th object has some properties, relations. But from the meta viewpoint, from the viewpoint of us, A is a triangle. You can all see that A is a triangle. And the 6th tuple is just a collection of 6 triangles. It's not a triangle. You know, it's kind of cheaty triangle, but it's not a real triangle. Well, it is confusing, and it gets more confusing, because in the world of mathematics, everything is a set. Like in the world of triangles, every object is a triangle. In the world of mathematics, every object is a set. And the confusing thing about this, even collections of objects are sets. You know, in this example with triangles, the collection of triangles wasn't a triangle. It was just a collection of triangles. But in the world of set theory and mathematics, reasonable collections of sets are sets. So you can see what the problem is. Okay, so how does a model of set theory look? Well, it's kind of cheating again, because first I would have to tell you what the axioms of set theory are. I will try to tell you a bit about axioms later, but let me give you just the basic elements of a model of set theory, or rather of a structure that, if it satisfies some property, can be a model of set theory. So ignore just for a moment this blue and red bubble in there, just concentrate on the black picture. So if I want to give you a model of set theory, I first have to give you what we call a universe. Universe is this V, it's this black bubble, and the elements of the universe are sets. It's just a universe. To make it a structure, I have to give you a relation, and if I want to make a structure that could become later a model of set theory, the only relation I have to give you is the relation of being an element, or the epsilon relation, or the membership relation, whatever you want to call it. So these are the black arrows. So if I have this picture A and 2 arrows to C and B, what I mean by it is that B and C are elements of A. That's it. And if I draw a picture like this, and the picture, well, the trouble is it would have to be infinite if I wanted to make it into a model of set theory, but whatever. If it's a nice picture, it can be a model of set theory. But the crucial thing is there are just these 2 elements to it, this universe and these arrows. So, from the first, let me talk about this meta viewpoint, because from the meta viewpoint, everything is simple. From the meta viewpoint, it means from the viewpoint of us as mathematicians living in the world of mathematics, where almost everything is a set, well then everything is a set. This universe V is a set. All those black dots are sets. This blue collection, come back to these colors, this blue collection is a set. Also the red collection is a set. It's just simple. Everything is a set. But what we are actually interested in how does this situation look from the viewpoint of the model. And what I mean from the viewpoint of the model, the usual metaphor mathematicians use is imagine you are being living inside the model. You cannot see anything else apart from what is in the model. So if you are living in this model V, the V, actually the domain, is not a set. It's what we call a proper class. And the reason for this is, or it may be put like saying it is too big to be a set. It's a proper class. It would take more explanation to explain the difference between proper sets and proper classes and sets. But it is, you may think of it, it's too big to be a set. So it's a proper class. Those black dots are the sets. These are the only objects there are from the viewpoint of the model. So these black dots are our sets. Now we might want to ask, what are these colorful bubbles? So with this red bubble, it is not that hard, because when I have a picture like this red collection, it's not an object of the model. Why? Because the only objects of the model are those black dots. And the red collection obviously isn't a black dot, so it's not there from the viewpoint of the model. So it doesn't make any sense to ask what it is. It's not there. The model doesn't see this. But the trouble is we have this blue collection, and in some sense this blue collection isn't in the model, just by the same argument as with the red collection. But you can see that this blue collection has exactly 2 elements, element B and element C. And if you look at my element A, you see that this element A has exactly 2 elements, B and C. So, in a sense, this element A is the blue collection in the sense of the model. Because it is, from the sense of the model, it is object of the model, and it has exactly the same elements. Okay? So what are the axioms of set theory? When I was reading Badiou, he says that mathematicians don't have definition of what does it mean to be a set. And that's perfectly all right. We don't have, and we don't worry about this. But in a sense, the axiom of extensionality can be thought of as a definition of what does it mean to be a set. Because what does this axiom say? It says if 2 sets have the same elements, then they are equal. So basically you can view this as a definition of a set, because the set is such a thing such that the only thing that matters for it is what elements it has. So it's not a definition we would dream of, but it explains what we mean by a set. So this is first axiom of set theory. Then we have a bunch of axioms of the following form. given a set or collection of sets, there exists possibly another set related to this given in a particular way. And example of this axiom would be Axiom of Pairing, which says if I have set, let's say B, and set C, then there is a set, let's say A, to fit it the previous example, such that its only elements are the sets B and C. So if I have two elements, I can pair them together and obtain another set. So, bunch of axioms of this form. Then we have axiom of infinity, which basically says that there exists a set such that it contains infinitely many elements, infinitely many other sets. And we have two axioms of foundation and choice. And I might comment on them if I have time, but I'm not sure about this. Okay, and this workshop or conference is about Badiou and about materialism. And when Michael asked me to give this talk, I tried to explain that, okay, I might do that, but I don't have anything to say about materialism. But I will mention materialism at this slide because it has to do with axiom of separation. At least Badiou says it has a relation to materialism. What is an axiom of separation? I might try to, I don't know if you can see here, but I might do, yes. I might try to draw a picture. Let's say we are given a set that is called, in this example, in this formulation, X. This is a set, and as most of the sets, it contains some elements. And then we are given some property that is this phi. This phi is just some property, and an element like this can either have or not have this property. So in a sense, I can divide this set X into two parts. In this first part, I have elements that have the property phi. And in the second part, I can have elements that have the negation of this property. And what this axiom says, it says that this first part, here, this actually forms a set Y. Okay? So if you don't want to read this formulation, you don't have to. That is exactly what the axiom says. If I am given a set, and if I am given a property such that it can divide a set, I can form a set from the first part of the elements that satisfy this property. So it is one of the axioms of the form I was talking about. Given something, there exists something else, usually. There is a very similar principle of comprehension, which can be shown to lead to contradiction. It basically says the same, but without supposing that there exists a set X. It basically says, if I'm given a property, there exists a set of all the elements satisfying this property. It can be shown to lead to a contradiction by Russell's paradox. And here comes Badiou, and his comment on materialism is a quote from Being and Event. And what does it say? He says that language cannot induce existence, solely a split within an existence. The split I draw by this curly line. Right? And he continues. Sermeo's axiom is therefore materialist in that it breaks with the figure of ideal linguistry, whose price is the paradox of excess, or you can think Russell paradox, in which the existence corresponds to what Badiou calls a situation. It's some multiple with some, let's say, operation count as one. And this operation count as one was what was represented by those black arrows, in a sense. Inconsistent multiplicity is multiplicity of the model. Because if we get back to this example of the red collection, I said the red collection is the viewpoint of the model. And it's my understanding this is the same thing, but he wants to say it is an inconsistent multiplicity. We cannot see it as an object.
Yeah. Sorry for interrupting you, but isn't this like blue belonging and inclusion?
Sorry, a belonging.
Isn't it like the belonging?
In the meta viewpoint, this red and blue bubble are subsets of the whole set V, and their elements are elements of the whole model V. So it's, I don't know whether it's what you mean. But
yeah, this whether something is included.
Yeah, there's a difference between
like the presence and representation
and being an element.
Yeah.
Yes. And a V, and let's say any one of these black dots is an element of this set V. Yeah. Okay. So, but he also uses the term consistent multiplicity, and he says it is a multiplicity after being counted as one. So I think, or it is my understanding, that we can view the blue collection that first was an inconsistent multiplicity after being counted as one as the element A. So somehow we get from the blue collection inconsistent multiplicity to consistent multiplicity, the element A. Maybe it's wrong understanding of Badiou, but it's the best I can give you. And this count as one is just what I described, just getting an element from a collection. Okay. So, this Badiou's mentioning materialism might evoke the idea that it is something materialist to just construct sets from already existing. Sets don't appear from thin air just because some already existing set to, give rise to a new set. So that might be a mathematician's understanding of what Badiou means by materialism in this context. And I want to show you something that is in set theory called von Neumann hierarchy of sets. It's a view of our universe, of our V, that was previously represented by this bubble as this big V. Again, I call it V. It should be the same V, just different shape. The universe of set theory from the empty set, or what Badiou calls from the void, or the void set. And done, but you need an axiom of foundation to do this. So it will be a mathematical discussion of what does it mean, why you need this axiom of foundation, so I will not comment on this, but it's a crucial thing. And how the construction works? Well, this first part, you just say it's just an empty set. And if I want to go higher, I say, well, to the next level, I put all the subsets of the previous level. Well, the previous level was just an empty set, and the only subset of an empty set is an empty set. So the next level contains as its element the empty set. So it already has one element, the empty set. Okay? And I go on. At the second level, I have two elements, empty set and a singleton of this empty set. And I have four elements, and it seems like, okay, nothing much is going on here. I might have, I don't know, 8 elements, 16. Oh, no. At the level 6, we already have so many elements that it's far, 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 far more than the estimated number of atoms in the observable universe. So this hierarchy kind of blows up very quickly, but it can be done. It gets much worse up there. And that's just what I said. It just said that you get the next level of the previous level. So it might seem that I have a way to construct my universe. I just start from the empty set universe of set theory. The one I construct from the empty set, it's very far from truth, because I can construct what is called Gödel's Constructible universe. It's a universe of set theory. It's a proper class that satisfies all the axioms of set theory, and in this sense it can be thought of as some other universe of set theory. And what is interesting about this is in a sense the smallest universe you can get in a set. So you just start with your V, you start constructing those levels and get the same. The first or the 0th level is just an empty set, the first level is just a set containing only the empty set, and so on. You also get a transfinite hierarchy. Before, if I wanted to construct V alpha plus 1, I would just take all the subsets of V alpha. Now I don't take all of them, I just take those that are definable in my language, which usually, not in general, but usually is much less. So if I'm down here, it's the same. It doesn't make any difference. But in general, here there, it makes a lot of difference. I get usually a proper subset of our V hierarchy. And this L an inner model as another model of set theory, living in an existing model of set theory, a bit thinner model. So there's, before I told you that we have basically two views, the view of the model and the meta view. Now we have already three views. The view of the model V, the view of the model of L, and the meta view. It's not. Okay. So should be ending. Okay, there's this construction forcing, which I will skip because obviously I don't have much time. But it is a way how to add a new set to an existing universe. So I will just show you this picture. Showed you how to get from our universe V, the black one, the blue one, universe L. You just forget about the subsets that are not definable in your language, and you get a perfect extent, even for mathematicians, is a way how to expand your universe. You just pick a set from somewhere outside of your universe and decide to glue it to the universe and expand your universe. You get something that looks like this red one, this expanding universe. So we already have in this picture 4 viewpoints. This black, blue, red one, and this meta viewpoint. And at this point you might think, okay, so obviously if I can keep switching those viewpoints, it's not a good thing to do. I might want to restrict myself to this meta viewpoint, but the trouble is, the meta viewpoint is just a viewpoint theory at another level. And at this another level, you can do the same thing. You can get your inner models, you can expand your universe. So basically the message of this talk is solid in mathematics, in a sense that we know how, like, mathematics tells us how the world looks like. No, it doesn't, because mathematics, on the contrary, in some sense, tells you there are many universes, and there is no way to pick the right one. Okay.